In this lecture, I'm going to speak about the cable element. Let's start with the catenary structure. Kate is a Greek word that means chain. So there are chain-like structures. An example of this structure is La Sagrada Familia. This is an iconic structure in Barcelona, Spain, built in 1936. At this time, the steel was not industrially available, and the constructions were done only with rock, stones, bricks. And in this structure, the loads are transmitted only by compressive forces. This is a picture of the Sagrada Familia. The Spanish architect Antonio Gaudí used the concept of the catenary, borrowed from the scientist Robert Hooke, to build this structure. Here there is an imagine of the catenary structure. These structures support only their own weight, and the forces between the elements, the bricks, are transmitted only by compressive loads. There is no moments and no shear forces. You can imagine that in 1936 there were not computer software to do finite element calculations. And the calculations need to be done by hand at this time. So Gaudí created a physical model, a hanging chain model, to design the Sagrada Familia. So this is the physical model. So it consists of cables, and these cables support weights. So when you put the weights, the cables adapt, and they will transmit the loads only by tension. So Gaudí invert this physical model by a mirror symmetry to create the model of the structure. So in the hanging chain model, the forces are transmitted only by tensions. And in the physical model of the Sagrada Familia, here, the forces are going to be transmitted only by compressive loads. Okay, let's go to the governing equations of the catenary cable. So this is a representation of the catenary. So we assume that is fixed by this point, and at this point it has a certain weight per unit of length, represented by this letter mu. The tensions in any point is perpendicular to the cable. These the tensions tension changes along the cable, and as always we are going to take an infinitesimal element. The length here is delta x. First, we are going to get the kinematic equations. So the kinematic equations are these ones. First, we have the length of the element that can be obtained by Pythagoras theorem. So this length is the square root of the catetes square. And by trigonometry, you can find that cosine of this angle is equal to dx over ds. And here v is the slope of the catenary at x, that is the derivative of the catenary shape with respect of x, and it is equal to tangent of theta. Next, we are going to derive the balance equations. So there are two balance equations. The first one is the equilibrium in x directions, so this is this one. And the second one is the equilibrium in the y directions. Let's start with the y directions. In the y directions, you have the tensions multiplied by sin of theta at this point, and the tensions multiplied by sin of theta at this point. These two forces, and these are balanced with the weight of the infinitesimal element. Mu is the weight per unit of length, so you multiply by ds, so this the length of this element here, you get the weight. So this becomes the equilibrium equations in the y directions. And then you can divide by delta x, or the x. And this term becomes the derivative with respect of x of t sin of theta. And this is going to become mu ds dx. Now we do the balance equations in the x directions. So in the x directions, there is no gravity acting. So only the tensions, the cosine component of the tensions at the both edges. So this is the two components, t cosine theta at one point, t cosine theta at the other point, equal to 0, no gravity. If I divide this equation by dx, then I can identify this term with the derivative of t cosine theta with respect of x. That is going to be 0. So these equations can be integrated easily. So it's just a constant. The integration is going to be a constant that is going to be T0. The physical meaning of this T0 is the tensions at a point of the catenary when the angle is 0. If the catenary reach a point of 0 angle, then this T0 is going to be the tensions. But notice that the tensions is not constant along the catenary. What is constant is t cosine of theta. After having these equations, I can replace these equations into these equations. So t is T0 over cosine of theta, and I am going to get these equations. So this converts into T0 tangent of theta equal to mu ds of x. So I still need to integrate this one. To integrate this one, I need to use the kinematic equations. So we have these equations, and notice that ds dx can be obtained from these equations. ds dx is 1 over cosine of theta. So I replace ds dx by 1 over cosine of theta. And using trigonometry, I can show that 1 over cosine of theta is equal to square root of 1 plus tangent square of theta. Now I have here tangent of theta that is already here. Tangent of theta is the slope of the catenary. So I'm going to replace tangent of theta by the slope of the catenary. So I'm going to get this one. So T0 is constant, thus it can go out of the derivative. Tangent of theta is the slope, v. And here tangent of theta is going to square, it's going to v square. And then I am going to get these equations for the slope of the catenary. This is a non-linear differential equations. It's not linear because I have here the slope square. Okay, the analytical solutions is easy to obtain for these nonlinear ordinary differential equations. So here I wrote again these equations here, and I just give the solutions that is obtained by direct integrations. It's in terms of hyperbolic sinus. And the C1 is a constant, integration constant. After obtaining the slope, you can integrate again, because the slope is the derivative of y, and we can obtain y, that is in terms of hyperbolic cosinus, and another constants. So we are going to get two constants that can be obtained by the fixed point of the catenary, this point and this point. And after applying these two boundary conditions, you can obtain the catenary shape. You still need to obtain the tension of the cable and the length of the cable. They are not provided by these equations directly. And so to obtain these ones, you need to get to the constitutive relations. Strand 7 provides a solution for the cable element in terms of the Young modulus of the cables and the initial length of the cable. So this is a flexible cable. So this includes some special case of the beam2 element in strand 7. This cable is a combination of the catenary that I introduced and the bar element under tensions, so that the length of the cable change according to the tensions and the gravity forces. So strand 7 calculates the length of the cable by dividing the cable into segments and using the incremental constitutive relations that is given by the Young modulus. This is the incremental stress and this incremental strain. This is in each segment of the cable. So I recommended that nonlinear static solver is used to obtain accurate solutions because this is a nonlinear equations. So this cable element works with static analysis only. For the dynamic analysis, the cable should be replaced by bars. But when you use bar, you need to check that all the cables are under tensions because the cables cannot work under compressions. When you run your dynamic model with bars, and if you find out that one of the cable is under compressions, one of the bar is under compressions, you need to correct this problem because bar cannot transmit compression. Well, bar can transmit compressions, but the cables cannot transmit compressions. In this case, there is an option in strand 7 is to replace the bar by cutoff bar. That is another case of the beam2 element. Cutoff bars in this particular case are bars that can transmit tensions only. Okay, this is a very typical questions in the cables of suspension bridge. This is a Golden Gate Bridge, and this is the shape of the suspension cables. So, is the shape catenary shape or parabolic shape? What do you think? Catenary or parabolic? And the answer is, okay, free hanging chains follow a catenary curve, like we saw. If the chains is, the only force in the chains is its own tensions and its gravity, then it's going to have a catenary curve. But suspension bridge cables, they don't hang freely because they are connected by cables, and these cables are connected to the deck. And these cables act mostly as a uniform distributed load that is much higher than the weight of the cables. So if the cable supports a uniform distributed load, it's going to adopt a parabolic shape. This is something that you can prove yourself by solving the governing equations of a cable with a uniform distributed load. So when suspension bridges are constructed, the suspension cables initially sag like a catenary curve, and then the cable gradually assume the parabolic curve as you tie the cables to the deck and to the suspension cable. The same principle applies for the Roman arches. In this case, the Roman arches are supporting a uniform distributed load, and the ideal shape is parabolic curves. And this is the end of the catenary story.